Welcome to The Explainer. I am absolutely thrilled you're joining me today because, well, we are tackling one of the most incredible, awe-inspiring, and just perfectly synchronized orchestrations of physics in modern engineering. We're talking about waking up a massive commercial jet engine. It's something that happens literally thousands of times a day around the world, completely seamlessly. Yet the sheer mechanics required to get these gigantic turbines spinning, absolutely fascinating. So strap in as we demystify the jet engine start sequence.
Okay, let's dive into this. Picture yourself sitting in a window seat on a commercial airliner. The doors are closed, you're just about to push back from the gate, and suddenly, you hear it. Right before the deep, thunderous roar of the jet engine kicks in, there's this distinct, high-pitched whine that fills the cabin. We all know that exact sound, right? But what actually is it? Well, that sound is an unsung hero of aviation going to work. It's the aircraft air starter. To really appreciate what that air starter is doing, we have to look at the massive difference in scale. Starting your car, it's a piece of cake. You turn a key or push a button, and a tiny electric motor easily cranks the engine to life. But a jet engine? No way. You're dealing with incredibly massive, heavy rotating components. A small electric motor simply isn't going to cut it for a large commercial jet. A jet engine needs a monumental external push just to get moving. Specifically, it needs a massive pneumatic push of high-pressure air. To understand how this all comes together, here is our flight plan for today. We'll cover the jet engine starting challenge, securing the pneumatic source, motoring the N2 core, fuel flow and ignition, reaching self-sustaining speed, and finally, monitoring for malfunctions.
Starting with number 1, the jet engine starting challenge.
So, the absolute fundamental rule of a jet engine is that it cannot start itself from a standstill. It has literally no way to pull in air on its own when it's completely static. And this brings us to the Brayton cycle, which dictates exactly how a gas turbine operates. Think of it as 4 simple steps: suck, squeeze, burn, and blow. The engine has to suck in air, squeeze it to compress it, burn it with fuel, and blow it out the back to create thrust. But to initiate this cycle, we must artificially spin the compressor to generate a massive amount of airflow before we can even think about introducing any fire into the combustion chamber.
Which leads us to part 2, securing the pneumatic source.
If we need a massive volume of compressed air to physically spin this giant engine before the start switch is even flipped, where exactly does all that air come from? Well, on modern commercial aircraft, there are 3 primary sources for this high-pressure bleed air. The most common? That's the Auxiliary Power Unit, or APU. This is actually a smaller, secondary jet engine, usually hidden right in the tail of the aircraft. It provides both electrical power and that vital compressed air needed on the ground. But if the APU is broken, and hey, it happens, ground crews will connect what's called a ground air cart. You might hear it affectionately called a huffer cart, and they plug it right into the side of the plane. Finally, once you have one engine successfully started, you can actually route its compressed bypass air across the aircraft to start the remaining engines. We call that a cross-bleed start.
Moving on to part 3, motoring the N2 core. Now, what's really interesting about this next phase is what happens when we're sitting on the flight deck and the pilot actually flips the start switch. The crucial point here is understanding exactly what we are trying to spin. The air starter is specifically connected to what's known as the N2 core. That's the engine's high-pressure compressor and turbine shaft. It is the incredibly heavy, dense internal machinery of the engine. The pneumatic air starter is attempting to physically turn this massive metal shaft to a very specific rotational speed.
And here is the precise physical sequence of how it goes down. The engine control unit commands the starter air valve to open. Boom! That high-pressure air rushes from the APU right into the air starter motor. Now, this starter is an engineering marvel all on its own. The incoming air hits an internal turbine inside the starter, spinning it up to an astonishing 50,000 RPM. But obviously that's way too fast for the engine, so a reduction gearbox steps that incredible speed down to about 5,000 RPM to safely, physically motor the giant N2 core.
Next up, part 4, fuel flow and ignition.
As the core begins to motor and span faster and faster, airflow through the compressor builds. We're approaching the critical threshold where all this momentum finally meets fuel and fire. And the scale of this operation, it's just staggering. Before a single drop of fuel is ignited, the engine core must be motored to roughly 14 to 20% of its maximum speed. To put that into perspective, on an aircraft like the ERJ, that's over 2,200 RPM.
We have to reach this immense rotational speed just to push enough compressed air into the diffuser and combustion chamber so that the spark can be introduced safely.
And this brilliantly illustrates what happens next. Once the core hits that massive target speed, we reach the intense phase pilots call light-off. Fuel is forcefully introduced into the combustion chamber. We're talking about an initial fuel flow of roughly 200 pounds per hour. That is about half a gallon every single minute. This fuel mixes with the massive volume of compressed air, the igniters spark, and boom, we have light-off. The exhaust gas temperature, or EGT, rapidly rises as the fire takes hold.
Section 5. Reaching self-sustaining speed. Let's see how this builds, because up until this exact moment, the pneumatic starter has been doing all the heavy lifting. But now, the engine's own combustion process begins to generate intense power, accelerating the turbine from the inside out. If you were acting as the pilot, watching the gauges spool up on the flight deck, you'd see the fuel flow initiate, you'd watch the EGT spike during light-off, and you'd see the N2 rotation speed accelerate even faster as the engine starts contributing its own power. But the air starter? It's still engaged, helping push the engine along until it crosses a very specific finish line. That finish line is roughly 40 to 50% N2 speed. At this point, the engine reaches a self-sustaining idle. It's now generating enough of its own power to keep accelerating without any external help whatsoever. The starter air valve automatically closes, cutting off the pneumatic air supply, and a clutch mechanism allows the air starter to physically disengage from the engine. The whine stops, and the deep, rumbling roar of the self-sustaining jet engine takes over.
And finally, Section 6, monitoring for malfunctions.
This incredibly high-stakes orchestration of physics happens in under a minute. And because you were mixing massive amounts of fuel, fire, and highly pressurized air, well, sometimes things go wrong. This is exactly why pilots, working alongside a highly advanced computer system called FADIC, which, by the way, analyzes engine data up to 70 times per second, monitor the parameters like hawks. They are watching for a hot start, where the exhaust gas temperature rises way too dangerously high. That requires the pilot to immediately cut the fuel and use the starter to just blow cool air through the engine. They're also watching for a hung start, where the engine rotation stalls and fails to reach idle speed. Or a no light-off, where the ignition simply fails to spark the fuel. In all these cases, the start must be immediately aborted to protect the engine from catastrophic damage.
But thanks to absolutely incredible engineering, stringent maintenance, and digital oversight, failures are rare. The entire violent orchestration of air, gears, fuel, and fire happens flawlessly beneath our wings every single day. The air starter truly is a marvel. It's a robust, dependable system that acts as the silent, or rather the high-pitched whining, enabler of the thunderous power that shrinks our globe.